Hello guys, welcome to my channel Amateur Technical. In today's lesson, we're gonna learn how to do the structural analysis of building using popular software available in the market. So here we're gonna learn how to do the structural analysis of the building as per NBC code 105/2020 in the popular software, that is ETABS version 20. Then we're gonna do the foundation design, that is isolated strap and combined footing in the software SAFE 20. And then we're gonna do this detailing of the reinforcement for beam and column as per the IS code 456-200 in the CSI Detail 18 software. And please do note here that the CSI Detail 20 will not work on ETABS version 20. So after that, we're going to do the analysis of the structure as per IS code 1893-2002 in the another popular software, that is StatPro V8i SS6. And then we're going to finally do the analysis of structure as per IS 1893-2002 code in the new software, that is Tekla Structure Designer version 22. So in the ETABS 20, we're going to do the analysis of the building and design. Here ETABS stand for Extended 3D Analysis of Building System. So in the ETABS version 20, there are three steps involved in the designing of the structure, and that is modeling, analysis and design. In the modeling part, we're going to define the material, section, diaphragm, load pattern, mass source, and do the drawing parts. And then we're going to do the assigning of the support, load, diaphragm, and also we're going to do the assigning of the base. But in case if we forget to do the assigning of mass, it is no problem, as the software do it automatically for us. And then after that, we're gonna define the load combination as per the NBC code 105/2020. So after modeling, the second steps comes with the analysis part. And in the analysis part, we're gonna check the bending moment, shear force and axial force diagram of the structure, and also we're gonna find the reaction of the structure, and we're gonna plot the response spectrum diagram. And here we're gonna also check the value of the story drift and displacement and check it if it doesn't cross the standard code value. And also we're going to check the center of mass and center of rigidity. At the center of the mass and center of the rigidity of the building should be less than 10%. And finally we're going to see the model participating mass ratio, where the first and the second node will be on the translating and the node third will be in the torsion part. So after analysis of the building, here we're going to do the designing part, and in the designing part we're going to calculate the area of the reinforcement and also check if the member is failed or is passed as per our analysis. So without any delay, let's start the modeling of the residential building in the popular software ETABS version 20. So now we're going to do the structural analysis of the building in the ETABS version 20. So I have already opened ETABS here. So here I'm gonna click the new model, but before going to the new model, I'm gonna give you some information about our residential building. So now I'm gonna open the AutoCAD. Here you can see this is the building which we're gonna design. So here you can see is the ground plan. It consists of the 3 rooms including 1 kitchen and a staircase. So here is the ground floor, then is the first floor, second floor and the terrace. So basically we have to input the grid system as per this dimension. So for our easiness, I have converted the feet and inches to the mm unit. So here you can see the unit. So the building which we're gonna design is a residential building. So here I'm gonna give you some information of our building. So the types of building is a residential building. The structural system is the reinforced concrete frame, and the number of story is ground floor plus 2. The ground floor height is the 2.84 meter. The story height is also 2.84 meter. And the soil type we're gonna use is the medium type D, and the bearing capacity will be 110 kilonewton per meter square, which we need at the time of the designing of the foundation. So other dimension we will talk in the ETABs during its input. So let's open the ETABs. So now here, go to the file and click on the new model. And in the AutoCAD, so this is our X direction and this is our Y direction. So here in the ETABs, in the model analyzation dialog box, select the use built-in setting width. So here the display unit will be metric SI. Region for default materials is India. The steel section based database also tick the India. You can select other one as per your requirement. The steel design code will go out with IS 800 2007, although we don't need this for now, but just select this. And the one that we need is the concrete design code, and that will be IS 456 2000. Click on the OK. And now in the other dialog box we have to set the grid. So here you can either go from the uniform grid spacing or the custom grid spacing. For this tutorial we're gonna use the custom grid spacing. So here select the edit grid data, and in the grid system data you can specify your grid system name. For now, in the rectangular grid, check this one, display grid data as spacing, and as per our AutoCAD dimension we're gonna input those values in the ETAB. So here you can see in the X direction the first unit is 3.4048 meter. So go to the ETABs. So in the X grid data we're gonna input the grid ID for A is 3.048, for B is 3.734 meter, for C is 3.785. So, and in the D, let it be 0 meter for the spacing. And the Y grid data, in the Y direction we have 1.524. Now then we have 3.048 and 3.912. So here you can see in the preview window also A, B, C, D, that is our grid. So it matches with this one. This assume this one is A grid, B grid, C grid, and D grid. And in the X direction we have 1, 2, 3, and 4 grid. So let's see here 1, 2, 3, and 4. And for the forward bubble size we're gonna do it 900 mm and click on the OK. So in the story dimension, number of story is G plus ground floor plus 2, that will be 3. A typical story height, as you mentioned in our report, that is 2.84, that is 9 feet 4 inch. That is typical story height, and for the bottom height is also same. So click on the OK. So here the ETAB we will show the grid as per our grid spacing data. So here we need long plus 2 floor. So let's go to the ETABs. I think it's taking some time. So here you can see our grid has been made, and you can also check the dimension if it matches with the AutoCAD dimension or not. So I think it matches. Okay, yeah, it's matched. So now here you can also modify the grid if the input value is wrong. So go to the add and modify grid, and here in the edit story and grid system data you can change the grid by clicking on this modify also grid system data, or you can also modify the story data by selecting this. So here the total height of our building is 8.5344. So once you have created the grid, the next step involved will be defining the material and the section property. So here in the menu bar you can see the define menu. So just click on this define and select this one, material property, and in the define material we're gonna assign the new material. So here the region is the India, the material type, since we are designing the reinforced concrete frame, so let's go to the concrete, and the standard is India, and for the grade we're gonna use M20 and click on OK. So once you hit the OK button, here is the material property data. For the material name we're gonna leave it as M20 and also leave it rest as it is, and click on OK. So here your concrete material is defined. Again hit the add new material, and in the add new material property, same as before, but for the material type click on rebar. So for the grade of rebar we're gonna select SYSD grade 500 and click on OK. And for the material name we're gonna keep the same SYSD 500 and click on OK. So since we are following the NBC 105 2000 code, let's check the material that we need for the building. So here it is specified that the grade of material should be, for the minimum grade of structural concrete should be M20, for M25 for building more than 12 meters in height. Since our height of the building is, here I have already shown you that the height of our building is 8.5334 meter, which is less than the value specified here of 12 meters. So the grade of the concrete we use is M20, and for the reinforcement we adopt grade FE 500. So I'm gonna close the code, and here I'm gonna again define the section property for the frame section. So in the frame section I'm gonna add a new property. So the section shape will be concrete rectangular, and the one we use is concrete. So in the frame section property type, the property name will be column 300 into 300 by 300, or you can like 12 inch by 12, whichever you like. So I'm gonna go with 300 by 300, and the material type which we have already defined, and that is M20. For the next one size data we'll leave it as it is, and for the shape with the concrete rectangular, and for the section dimension the depth we're gonna go with 12 inch, that is 304.8 mm, and the width also 12 inch. So here in the property modifier, first before going there I want to show you something. So the effective stiffness of crack section. So what I'm trying to say is, for the modifier as stiffness modification factor, we're gonna use the value for the shear and for the shear and for the flexural stiffness. For the column we're gonna use 0.7 and 0.4. So in the ETAB, For the shear section, I'm gonna go with 0.4, and for the column we're gonna go with 0.70. So what we have done is we have assumed the crack section for the column, and we're gonna do it for the beam, so which will accurately depict the condition of the reinforcement concrete during the earthquake force, or at the time of the earthquake force loading in the site actual. So by doing this, we have considered the cracked portion of the concrete. So click on the OK button. So here in the reinforcement, click on the modify and show rebar. So for the design type, since we are designing the column, so select on this one. For the longitudinal bar, we're gonna go with 500, and same for the confinement bar. And for the reinforcement configuration, we're gonna select the rectangular, and for the design check, let it be reinforcement to be designed. So for the clear cover, as per the IS 456 2000 code, we're gonna keep the clear cover 40 mm. Number of longitudinal bar along 3 direction face will be 3, and for the 2 direction face 3. And the corner bar size area, we're gonna select 60, and for the longitudinal bar area, we're gonna go with 12. And for the confinement bar size and area, we're gonna go with 10, and click on OK. So after that, just click on OK, and our column data is finished, or the property of the column is finished. I'm going to copy the same one and click on the add copy or property. So it is taking some time, but you have to be patient. So the property name will be beam of width 250, or you can 9 inch to 30 into 350. For the materials, we're gonna go with M20. Here I'm gonna show you the sites which we have agent. For the beam side, we're gonna go with depth of 350 and width of 230, and the column size is 300 by 300 mm. So depth is 350 and the width is 230. And here you can check for the beam, the flexural stiffness is 35 and shear stiffness is 40. So go here, and for the flexural stiffness 0.35, and hit the OK button. And for the reinforcement, now this time the design type is for beam, rest is same, and for the clear cover we're going to go with 25 mm. Click OK, click OK. Now here you can see our beam property has been defined. Again click OK. So after defining the beam and column property, we need to do is define the slab property. So click on slab section, and here we're going to use this one, and we're going to modify the property of it. So then will be same. The thickness of the slab is 125 mm. Thickness, here in the property data we have kept the thickness 125. Let's leave it as it is, but the slab material we have to choose the M20. Okay. So after defining the property for the beam, column and slab, the next thing we're going to do is we're going to define load patterns. So here there is mainly 3 type of load act on the building, that is dead load, live load, and the earthquake load during the time of the earthquake. So basically the dead load, the software automatically take the value or I mean the weight of the beam, column and slabs. So we have to leave it as it is, so the one denote it. For the live load, we're gonna keep the value as per the NBC 105 2020 code. And for now, we're gonna define rest of it. So there are many load that act as a type of date load, that is wall load, partition load, floor finish load, staircase load. So wall load, the type will be date and self multiplier will be 0. Again, we can add another one, that is partition wall load, same as wall load, that is type date. Then we're gonna add floor finish load, same as before, date, states date, type will be date and multiplier will be 0. Then there is stair live, type will be live or is same. If you want to change anything here, just select that and modify the load. So after stair live, we're gonna define water tank load, that will be also live load, and then we have to define earthquake load. So as per the NBC code, we have to define the earthquake for the ultimate limit state and for the serviceability limit state. If you are designing this structure as per the IS 1893-2000 code, then we have to only consider earthquake load in the X direction and the Y direction. But the NBC code, which has been revised from 2020, consider that we have to take both the ultimate and serviceability limit for the load combination. So now for the earthquake load in X direction for ultimate limit state, at a type will be seismic, and auto load later will be user coefficients. Since NBC code is not considered in this software, only IS code has been considered, that is this one. So for the NBC code, we have to select the user coefficient and click add new load. So same as in the Y direction, click add. For X, SLS, add. For X, Y, SLS, add, and click on OK for now. So we have defined the load pattern. Now let's check the load case. So here the one we have defined just before is already added in this load case. So click on load. Okay. So before defining the load combination, let's check the theory. So if you are designing the building as per the IS code, then we have to compute the base shear, that is VB, and the formula for it is, here you can also use in this code. The total design lateral force or design seismic base shear VB along any principal direction shall be determined by the following expression, that is VB is equal to H into W. H is the design horizontal oscillation spectrum, that is seismic coefficient, and W is the seismic weight of the building. So for the AS, we compute the value of AS from this equation. H is equal to Z by 2 into I by R into SA by G. This value you will find in the code in the table. For the zoning factor, you can use the table too, and same goes for the importance and this importance factor I, and here you can see the importance factor I, and for the response reduction factor R, you can use this table value as per your building frame system. So since we are not designing as per the IS 1893-2002, we are designing as per the IS 456. Sorry, we are designing as per the NBC 105-2020 code. So this code states that for the base shear calculation, we have to consider two formula, that is for ultimate limit state and the serviceability limit state. So here you can see the design we are going with is the equivalent static method. Since the building configuration is of ours is the parallel system, here you can see here for the building system is our parallel system, so this will be the combination. And for the equivalent static method, we're going to use these two formula. CDT1 is CT1 divided by R mu into omega mu. And the same for the service limit state, where CDT1 is CST1 divided by omega S. So to find out this value, I have an Excel table where I'll explain it. So for the seismic coefficient as per NBC, the location of our building, just say is in the Nepalganj. So here you have to select Nepalganj, and it will consider the zoning factor as per this location. But now we're gonna do only for the Kathmandu value. So I'm gonna get the Kathmandu and select it. Yes, it's Kathmandu. And the type of the structure is the residential building. The structural analysis method we're gonna use is the equivalent static method. And the zoning factor for Kathmandu is 0.35. Here you can see in the clause 4.1.4 of the NBC code. Here it's after the Kathmandu value, the zoning factor is 0.35 as per the clause 4.1.4. And the important factor I is 1, and height of the building is 8.534. I have already shown you in this value in the ETAB. And the soil type is the B, and type of frame we're going to consider is the moment resisting concrete frame. And for this we're going to go to this class and find the value of KT. So as per clause 5.1.2, that is empirical equation, the value of KT for the moment resisting concrete frame is 0.075, and amplification of the approximate period will be 1.25 times this value. So here we have considered this one. So after computing, the value comes 0.468. That is the fundamental period of vibration T1. So after getting this value, let's go to the clause 5.1.2 and 3. Or you can also go to table 4.1. This is table 4.1.2 4.1. So here the value of TA for the equivalent static method is taken at 0. So here you can see is 0. If our structural analysis method was dynamic analysis, then value will not be 0. So since it is equivalent static method, the value of TA is 0. Now let's check the value of T1. Since the computed value of T1 is 0.468, let's go to this equation. Here it is said that if T1 is less than TA, then we have to use this formula. But if T1 is greater than TA and less than TC, then the value will be alpha, and that is the value of alpha is 2.25. But in case if the value of T1 is greater than TC and less than 6, then we have to use this formula. So this value satisfy the value of 0.468. You can see it satisfy this one alpha, since it is less than TA. Although 0.648, So I'm going to open the both window and compare it. So value of T1 is greater than TA, since it's 0, so it's greater than TA, but less than TC. The value of TC as per the table form 1 is 2 for the soil type T. So here you can see the value of TC is 2. And our peak spectral acceleration normalized by Pj alpha is 2.25. So after computing, we get the coefficient K is 0.8. This one. Okay, so now the spectral factor CST is let's 4.1.2. So the spectral factor CST is 2.25. That is, since this equation satisfies this second one, so our value is 2.25. And for the elastic side spectra for horizontal loading, that is CT1 is CST into Z into I. So CST we have value 2.25, Z 0.35, and I we can see here is 1. After computing that, we get a value 0.788. So here you can see in class 4.1.1. So this is the equation for elastic side spectra. And for the elastic side spectra for SLS state, we're gonna multiply this computed value with 0.20, which you can see in the class 6.4.21. Sorry, class 4.2.1. That one is this one, 4.2.1, this one. So now we need to compute the horizontal base shear coefficient. So as discussed before, the horizontal base equation is found in class 6.11. So here this is for the ultimate limit state. The horizontal base shear coefficient at the ULS state CDT1 is this one, CT1 divided by R mu into omega mu. So by computing this value, we get the value of CDT1 is 0.131, and for the limits service limit state, we get the value of this one. You can find RU and mu in the table 5.2. So once you get this value, we need to compute the exponent related to the structure period K, which is stated in the class 6.3. So in the class 6.3, okay, for the structure having time period T is less than or equal to 0.5 second, the value of K will be 1, and if it is greater than 2.5 second, the value of K will be 2. And if the value of T lies between 0.5 and 2.5 second, then we have to do the value of K with the help of interpolation between 0.5 second and 2.5 second and 1 and 2. So for now, the value of our K is 1, since this 0.468 is less than 0.5 second. So you have to remember this 3 value. So now we're gonna go into ETABs. So under define, go to the load pattern, and here we have already specified the load for the earthquake. So select this one, EQX ULS, and under user coefficient, select modify lateral load. So here since it is the earthquake load in X direction, we're gonna untick this one, and for the eccentricity ratio, so that you will find in the class 5.7. The accidental eccentricity is 0.1. Taken at 0.1, not 0.05. That will be in the IS 1893 code. So the base shear coefficient for the limit state is 0.13. Let's check the Excel. 131, and the value of K is 1. Click on OK. And same for the Y direction. untick this x direction and select this y and go to 0.1, and where coefficient will be 131 and the value of k will be 1. And similarly for SLS, modify the load pattern in the x direction, untick this y direction, and the ratio will be 0.1. This will be for substituted limit 0.126 and k is 1. Okay, and for the x direction, uncheck this one, y direction, and its ratio will be 0.1, and the shear coefficient should be 0.126, and the building height exponent k is 1. Okay, and click on OK. So till now we have defined the natural section property of the beam, slab, and the column, and the load pattern. So in the next video we're gonna define the load combination, and we're gonna input the loading data here by first drawing the column and window, and then first drawing the column, beam, and slab, and then loading it with the dead load and earthquake load data. So for now, this much. We're gonna see you in the next video. Thank you.